Okay, so let's take a look at a couple of graphing of rational equations that are a little bit more complex and just in the way that they don't have horizontal asymptotes. I have one that has a slant asymptote, like a linear asymptote, and one that is non-linear. And we'll kind of see both of those. Hopefully it was going to go reasonably quickly because I have most of it set up. So anyway, let's go ahead and take a look at those from the start. So here we go. We're going to begin with this function right here. Now, I wanted to start with something where structurally it was set up pretty well in two different ways so we can see it. You can see that I have a third degree divided by a second degree, which is going to make it a slant asymptote. So there's a couple of things that I want to put in very early. You're going to notice that there is no removable discontinuity because there's nothing in common between the top and the bottom, which is going to leave me with a vertical asymptote at negative 1, 2, 3. And another vertical asymptote at 2. That's a known, those are a couple of known facts. We also have a root at negative 1, a root at positive 3, and a root at negative 4. 1, 2, 3, 4. A root at negative 4 right here. And last but not least, if we were to plug in 0 for x, I can see a y-intercept of the number 2. So again, there's little tricks that we can see because quite literally these three places, because this is a third degree equation, these three places right here are literally the only place this curve can cross the x-axis. So what I can tell almost immediately is for the graph to go from here to here, it's going to have to be something that curves like this, but we'll get that information over time. So let's jump in here into the middle and get a little bit of data that we know. So the first thing that I know is that if I plugged in a number to the left of negative 3, like negative 3.1, every single one of these two values would both be negative, right? Negative 3.1 plus 1, negative 3.1 minus 3, negative 3.1 plus 4 is positive, and negative 3.1 plus 3 and this one are both negative as well. So this thing is going to positive infinity here. So that's a good little fact. When we jump to this one, all of these data values are going to actually be the same, except for the piece that provided this negative 3 as an asymptote, which is this guy right here. So if I plugged in negative 2.9, that little piece would change to a positive from a negative. Nothing else would change. And so I know it's going down here on this side, which kind of confirms what I mentioned is that I thought it might be an S-curve. Now, moving on a little bit further, if we plugged in, say, 1.9, all of these, this value would be positives, but this value would be negative. At 1.9, this value would be positive and this value would be negative. Now, again, as I slide over to here, all of these numbers are going to stay the same except for the piece that provided that one, and that was right here. So notice if I went to the higher side of 2, like 2.1, that one would be positive. So it looks like that cumulatively became negative because I only had one negative asymptote. So I think I've got all the pieces that I needed. I had an up here and I had a down here. I think is what we said, yeah. And so I could play connect the dots. It's going to go something like this. There's a down here and an up here, but now we've got to do the hard part of the problem. And this is the part I was waiting on. I have this third degree equation and I need to either do long division to divide this out to get my first degree equation, or I can do synthetic division twice, which generally speaking, you guys have kind of liked the synthetic division version better. So I'm going to use a little bit of a hybrid of these two things. I'm going to take 1, 2, 1x cubed, 2x squared, 11x, and 12, and I'm going to divide them first by the number negative 3. So I'd get 1, which 1 times that would give me negative 3. Negative 3 times negative 1 is going to give me positive 3. That's negative 8 and 24. And you're going to notice that that didn't divide in perfectly. So I'm not worried about it. So technically, when I divided by x plus 3, I got x squared minus x minus 8 and some remainder that we're not going to worry about. But now what I'm going to do is I'm going to take what I have left and I'm going to divide it by this other piece, which is 2. When I drop the 1, I get 1 times 2 is 2. That's going to make a 1, and 2 times 1 is 2. Again, leaving some kind of a remainder. So I'm going to cancel that out because we don't need it. What is left is an in behavior asymptote of y equals x plus 1. So here we go. If we were to graph x plus 1, that is a nice slant asymptote cutting through this problem about like this. I just did enough so I'd get a good feel for it. And so in order to make all this make sense, the graph has to get close to this asymptote. It has to touch this point and it has to get close to this asymptote. So the only way that this can do that is some kind of curve coming this way. But similarly, the only way I can get close to this asymptote and this one is if it swooshes down this way. Now, I did think about bringing that up in a Desmos window, and maybe I should go ahead and do that so we can clarify and make sure that what we did makes sense. So let's go ahead and let's try that. So let's see what happens when we check out our question in our good old friend Desmos. So I actually had this problem typed in earlier today, but I didn't get around to actually doing it and I messed it up. So I had my original problem divided by x squared plus x minus 6. So there's my curve. We figured that we had a vertical asymptote at x equals -3, which looks good to me. It looks like we thought we had an asymptote at x equals 2, a nice another vertical one that looks like we did okay here. And last but not least, we thought we had a slant asymptote at x plus 1. And if you look at that one, again, making it dotted and I'm making all of the asymptotes blue, you can see is that I scroll out and show what it looks like. All of those bells and whistles that we thought it was seem to be appropriate. Okay, so let's go back to the question sheet that I have here because I had one more to look at. Now, this problem, in a sense, might look like it's a little harder because it's a third degree, sorry, that's an x cubed, divided by a first degree, and a third degree divided by a first degree is a second degree. So this is a parabolic asymptote. Now, what I did is I came over here to the side and I front loaded this to make it faster. I had 2x cubes, no x squareds, 4 x's, and a constant. I divided by 2. And so 2 times 2 is 4. Add gives me 4. 2 times 4 is 8. That gives me 4. And again, this is my remainder, which we're going to throw away anyway. So I have this nice little parabola, which is y equals 2x squared plus 4x plus 4. And as you recall, any parabola that has a leading coefficient that's positive is going to end up at positive infinity. Now that's weird because it's not positive infinity going flat, but positive infinity then going up. Now, similarly, if I picked any number anywhere near the number 2 that you can see right here, 2 cubed is 8. 8 times 2 is 16. 4 times 2 is about 8, but no matter what, that number is some kind of a positive value. That's not going to change. Any number in the neighborhood of the number 2 is going to be positive. But if I'm slightly below the number 2 that this asks for, like 1.9, I had a negative, or above, I got a positive. So this one is going up, this one is going down. And so we can now start building our function. I've got a vertical asymptote here. It is going up on this side, down on this side. A couple little things that I noticed is if I plugged in 0, I got -1/2. Again, just the y-intercept. Now, I did play with my parabola over here. I factored the 2 out, leaving x squared plus 2x. Then I cut this in half and squared it, and I got 1. And 2 times 1 is 2. So that left me with a -2. And so evidently I made a big boo-boo there. I just realized that I did, but I fixed it now. So I completed the square. So again, keep in mind, I factored the 2 out, which would give me 2x squared plus 4x plus 4 still, like it said. Cut in half, 2 halves is 1, squared is 1, but 2 times 1 is 2, balancing. So I added 2, I subtracted 2, and we're good to go. So my vertex is at negative 1, 2. And this is my parabola, but instead of using a 1, 3, 5 pattern, it's going to be a 2, 6, 10 pattern because it's been doubled. So I'm going to go over 1 up 2, over 1 up 6. This graph is phenomenally steep, way up here like this. And so what you can see how this is going to work is the graph, as it turns out, because it ends up, I wish I had picked a much better scale. Since it ends up at infinity, it's going to have to come up and go like this over here. And on this side, it's going to have to loop in here and cruise right along the side of that parabola. Okay, again, I wish I had picked a slightly different scale, but I'm going to go over here back to Desmos and let's make a look at it, and maybe we can make it look a little bit better. So again, like we said, we had 2x cubed on top. We had a minus 4x on the bottom next, minus 4x and a plus 1, okay? And the denominator was simply x minus 2. So we had this curve right here, and that mine looked a little bit more smooth. I didn't realize it came up as high as it does. We realized that we had an asymptote at x equals 2, just like the previous problem. I think I do that a lot. And I got a slant asymptote at 2x squared plus 4x plus 4 is what I think I said it was. Now, if we zoom out, I think what we're going to see is the graph does, in fact, on top get very, very close like I thought it did. It's kind of weird. It's way high up there. I think I would like to pick a different window of maybe negative 10 to 10 and maybe let the y values go as low as maybe negative 50 to 100 maybe. And I think that's a pretty good window to get a good feel for what this particular graph looks like. And it in fact does hug that parabola quite well. So hopefully that's helpful. It does have the y-intercept that I mentioned, but it's hard to see these x-intercepts because it was a third degree equation that I didn't have factorable. So those were not nice numbers to determine those x-intercepts. But hopefully that was a little bit helpful. And like I said, I will see you back in class if you have any questions. Bye-bye.